Okay, so last class we started root locus. We played around with changing our value of our k gain and seeing what that did to our poles and our zeros. We started plotting the root locus, so we started to show that we know that the poles and zeros that we put on our root locus as x's and o's, those are our open loop or closed loop poles and zeros. Open loop, right? And then we had these things called branches that are those solid black lines. In MATLAB, they have pretty colors, but for me, they're solid black lines. And those are what? Open loop or closed loop poles? Those are the closed loop poles for all the values of k from 0 up to infinity, okay? And then we talked about a couple of different criterions that can answer a couple of yes or no questions. One yes or no question and one question about the k gain. So the first yes or no question is, if I have a value on the S-plane, is this value coincident with the root locus? So is it on the root locus for any value of k? And using the angle criterion, we were able to answer yes or no. Okay, we didn't know what value of k put it there, but we could tell yes or no it was on the root locus. And then we talked about the magnitude criterion, which told us exactly what value of k put that point on the root locus. Okay, we did not go into sketching the full root locus, but of course that's what we're going to work on today. Okay, there are a set of rules that will govern how we draw the root locus. I'm not going to go into proving why each of those rules is the case, although I am aware that they exist in your book, and if not in the chapter, I think there's actually additional proofs in the appendix in case you're crazy interested in why root locus works. However, one of the things I want you to recognize today is that MATLAB will draw your root locus. Okay, so this is a skill that I want you to practice because it's good for you to know to be able to think and sketch the root locus quickly without a computer in hand. However, if we get to the point where we need like very intimate details about our exact root locus, the engineer in you should say, I'm going to put this in MATLAB, okay? There's probably some Python tools that will also do this for you, but as mechanical engineers, we love our MATLAB. Okay, so I'm going to show you how to do it in MATLAB. I've kind of already shown you, but today we're going to also talk about sketching it without MATLAB. All right, so as we talked about last class, we know that in order to draw the root locus, we could do things very ritualistically. We could mechanically plug in every value of k we're interested in, trace the root locus for each value of k. That's obviously extremely tedious, especially without a computer. Okay, the way that we're going to do it today is based on rules that come about because of the angle criterion. So remember, the angle criterion tells us whether or not a point is on the root locus or not. And from that angle criterion, we're able to determine a set of rules that help us find all of the points that are on the root locus. All right, so let's go into these rules. If you weren't here earlier, I did announce that the notes are already posted online. They are really wordy today. So if you don't feel like trying to rush to keep up with how fast I write, or if I have sections that I'm actually not going to write in real time, you can refer back to the notes online. You can take notes on the notes online. Whatever it is you want to do, that's fine. But they're posted and ready for you so that you don't have to feel like you need to keep every word that I write. Okay, the root locus rules. First off, we need to know, first off, the first thing we should do are put our open loop poles and zeros on our root locus map. Okay, so zeros are little O's, X's are our poles. But after that, after we have that kind of groundwork set, we need to know the number of branches that exist. Okay, the number of branches is fairly easy, and it's kind of intuitive that the number of branches, of the root locus is equals the number of closed loop poles. Okay, simple enough. Find your closed loop transfer function, find out how many poles it has. that's how many branches exist. Another rule is that these things have a sense of symmetry. Do you think they are symmetric about the imaginary axis, left to right, or are they symmetric about the real axis, top to bottom? Real axis, top to bottom, right? Because when we take roots of a polynomial, we often get imaginary poles that are plus and minus the same number, right? So we get one up and one down. So there's this symmetry, okay? The root locus is symmetrical about the real axis. Okay. And then we get information about segments of the branches that lie on the real axis. Okay, so sometimes these branches are going to shoot off into infinity, left and right. Maybe they'll go off at an angle. Maybe they'll even loop back around in a circle. But other times they will go directly along the real axis. And there's a very kind of fun rule for how we figure out what parts of the real axis are covered by a branch of the root locus. And this rule says that the root locus, let's say, how does it say it? On the real axis, for k greater than 0, the root locus exists to the left of an odd number of real axis finite open loop poles and or finite open loop zeros. The real gist of what this is once you have your poles and zeros, you put the branch on the real axis to the left of an odd number of O's or X's. So you have real axis poles to the left of a single zero. Then after that, it's to the left of 2 symbols, so you don't have it. After that, it's to the left of 3 symbols, and you do have it. It's very kind of simple to go branch, no branch, branch, no branch, branch. Okay, and don't worry, we'll do examples to solidify what this means. Okay, on the real axis, for k greater than 0, the root locus exists to the left of an odd number of real axis finite. I am saying this in a weird way because you probably don't know what a finite open loop pole is, but we're going to cover it in just a minute. Open loop poles and or finite open loop zeros. It turns out that you have what are called finite poles and zeros and infinite poles and zeros. And I'm going to go ahead and cover step 4, but in step 5, I'll explain exactly what is a finite versus an infinite polar zero. Okay, so let's go ahead and do step 4. Rule 4 is the starting and ending points of each branch. Which says that the root locus begins at the finite and infinite poles of G of S, H of S, and ends at the finite and infinite zeros of G of S, H of S. Okay, so each branch starts at an open loop pole, each branch starts at a pole and goes to a 0. Starts at a pole, ends at a 0. Okay? A good next question would be, well, Dr. Higgins, what happens if you don't have the same number of poles and zeros? Yes, we have infinite poles and zeros, which means that, yes, it may not be in the open loop system, but that means that that branch extends off into infinity as k goes to infinity. And we can figure out exactly how many branches do this according to our next rule. Okay, so we're going to talk about behavior at infinity, which is one of the more complicated rules. And in fact, I'm going to use a little bit of an example to help us make it concrete. So let's consider an open loop transfer function. We'll say G equals K over S, S plus 1, S plus 2. What are my finite poles? Well, your finite poles are the poles you're used to telling me about. So what are the poles of this transfer function?
0, -1, -2.
Great. So my finite poles are 0, -1, -2. Do I have any finite zeros? No, I don't have anything in that numerator that would cause it to be 0. So finite zeros, none. Okay, let's define what our infinite poles and zeros are. Infinite poles. Okay, if the function of S, if the function approaches infinity as S goes to infinity, the function has a pole at infinity. And then we have infinite zeros. Isn't there a band called like something something in the infinite zeros? I swear there is. I was thinking of it last night and I was like,
The magnetic zero?
oh, maybe I'm thinking magnetic zeros. Anyway, I was like, oh, I love that. That's so nerdy. Anyway, if you want to start a band, it should be like the infinite zeros. All right. The infinite poles. All right. If the function approaches 0 as S approaches infinity, the function has a 0 at infinity. Okay. In this way, we have a very interesting property, which says that every transfer function, function of S, however you want to say it, every function of S has an equal number of poles and zeros, as long as we consider both finite and infinite poles and zeros. Okay, so that means that if we look at this transfer function example here, there's actually two ways that we can show that we know that there have to be 3 infinite zeros. One is that we have 3 finite poles, and we need to have an equal number of poles and zeros. right? So if we add up finite and infinite poles, we need the same number of finite plus infinite zeros. We know there's 3 finite poles, no infinite, or, well, there's no infinite poles. So we know there must be a matching number of zeros. And since they don't exist as finite zeros, they must exist as infinite zeros. Yeah, John?
So some of the rules apply to open loop, some to closed loop. So I guess would we be sort of messing with the transfer functions to see if they apply to certain rules?
Yes, you will. However, for the most part, so the number of branches equals the number of closed loop poles. For the most part, your open loop poles are going to be the same number as your closed loop poles.
Okay.
Yep. So for the most part, we're talking about, I guess, open loop. Which kind of makes sense, right? Because we know that our branches have to start at poles, and they have to end at zeros. So they have to exist, right? There has to be a place for them to start and end, these branches. And so they're either finite and we can put them on the plane, or they're infinite and we draw that branch going off in infinity. Okay, so let's see. For the other way that we can look at this and know that there are 3 infinite zeros is we can see that as s goes to infinity. So what if we plugged in infinity here, infinity here, infinity here? Well, what is infinity plus 1 really? It's just infinity, yeah. What is infinity plus 2? It's really infinity. So when we plug in infinity, we really get something like k over s cubed, because those poles are all like very, very, very close to infinity. So each one of those infinities, dividing any number into an infinite number of parts, is going to make all those parts really, 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 really tiny. They're going to go to 0, right? So each one of these s's independently is going to cause this whole transfer function to go to 0 as s goes to infinity, which is the criteria for our infinite zeros. So as s goes to infinity, g becomes k over s cubed, and each s, as it goes to infinity, causes g to go to 0. So this function has 3 infinite zeros. Yes?
When you specify that each s causes it to go to infinity, is that because like we could also have had like an s in the numerator, and you just want to like be specific on which s's you're talking about? Okay.
Yep.
So like, would you ideally do this like separately if you had like multiple s's? But since they're all in the denominator, could we just say like, oh, you know, they're always going to go to 0? Like if you had an s in the numerator, would you have to like plug that one in separately without plugging in infinity for the the denominator?
I believe that's correct.
Okay.
But in practice, for the most part, what this equals out to is like the total number of poles has to equal the total number of zeros, and for the most part, we can tell just based on that, without really needing to look at and plug in s equals infinity. We know that if we're missing a if there is a finite zero, we know there still have to be 2 infinite zeros, because we need a place for these pole branches to go to, right? So for the most part, that's what we rely on.
But if we had like 2 finite poles, 2 finite zeros, like can you also just like deduce from that? Like you don't have to actually just go ahead and plug it in, or
For the most part, yes, but
You can still have those 2 more.
yeah, my question there is, if you have an infinite pole that you don't know about until you plug in, yeah, so you would have to plug in s goes to infinity to figure out about an infinite pole.
okay.
In order to know that it needs to be balanced by either a finite or an infinite zero.
Okay.
Yeah. Okay. Okay, so we now know, let's see. We know how many branches there are. We know that they start at poles and they end at zeros. Yep.
it's positive infinity or negative infinity?
It's always positive infinity because you're plugging in, you're trying to figure out what happens as k goes from 0 to infinity, which is directed to the positive infinity. But it doesn't matter because of the symmetry, right? So if you have a pole that's going up to positive infinity, there has to be one going down to negative infinity as well because of the symmetry rule. Okay, we know how many branches. We know they start at poles and end at zeros, be they finite or infinite. But there are lots and lots and lots of different ways that we could shoot off to infinity, right? Like all the rays of the sun. We could shoot off this way, that way, this way, that way, that way, that way, all of the different directions. So there are additional rules about the direction that those infinite branches shoot off at, okay? So that's this next set that I don't want to write out in real time. So it's in the notes. You can copy it later. The root locus approaches straight lines as asymptotes as the locus approaches infinity. So further, the equation of the asymptotes is given by the real axis intercept, sigma A, and angle theta A as follows. So you have two equations. Really, it's just plug and chug here. So you take the sum of your finite poles minus the sum of your finite zeros over your number of finite poles minus your number of finite zeros. That gives you your real axis intercept. Keep in mind I'm saying real axis intercept, which is a little bit strange because you're getting basically the x-axis intercept, which is a bit odd for a line. We're used to seeing the y-axis intercept, the y-intercept, but this is, anyway. Real axis intercept, sigma A, and then the angle that the asymptote makes with the positive real axis. So here is theta A. And we can do this for k values from 0 essentially up to the number of infinite branches minus 1. So however many branches we need to account for, we continue to plug in increasing values of k until we know all the angles that those asymptotes exist at. And again, I think an example is going to help solidify that idea. Okay, let's give this a try. I also want to explain right now that the 5 rules that I just explained, I'm going to categorize those as rough sketching rules. Okay, so these are the 5 rules you need to know to get just a very rough-grained idea of what this root locus looks like. There will be more rules after this, after we cover these first 5, after we do a couple examples, that help us to refine that root locus a little bit more. So that refinement might be like, okay, exactly where do these branches leave or return to the real axis? After these first 5, we'll know that they do leave and return to the real axis, but we won't know exactly where. So just foreshadowing for the next section. All right, so let's do an example of the rules we've looked at so far. So here we're going to do example 1, sketch the root locus for the following system. I've got just a forward gain G, which is k times s plus 3 over s times s plus 1 times s plus 2 plus s times s plus 4. So let's go rule by rule and see what we can figure out about our root locus. So I always like to start with number 1. Seems like a good place to start. How many branches do you think that we have? Well, the number of branches is equal to the number of closed loop poles. So John, I'm going to go ahead and show that our closed loop poles is the same number of poles as our open loop poles. So obviously this is our open loop G. Closed loop G is all of this mess. S plus 3, s plus 1, s plus 2, s plus 4, over 1 plus all of that mess. Okay, and friends don't let friends leave fractions in the denominator, so I can multiply by this thing on the bottom, this thing on the bottom. S plus, that's not nearly enough room. This should give us k s plus 3 over s plus 1, s plus 2, s plus 4, plus k s plus 3. Okay, so what after, I'm not going to FOIL all this out, which would be a massive FOIL, but let's think about it. How many s's am I going to multiply by at the end here? What will be my highest power of s in this denominator?
4.
Yeah, 4. So I have this times a this times a this times a this. That's 4 s's that are going to get multiplied together. Is this little piece at the end, is that going to raise the highest power of s at all? No. So the highest power of s in the denominator will be 4, which means that I have how many roots? 4. How many poles did I have before I did the closed loop transfer function? 4, right? So I have the same number of poles for both the open and the closed loop. Okay? Okay, so we have 4 branches. Let's even go ahead and start to draw this. Let's go ahead and put my open loop poles. I've got 0, minus 1, minus 2, minus 4. So I've got 0, minus 1, minus 2, minus 4. So poles, I have one open loop 0 at minus 3. Right here. I have 4 branches that need to exist, and I have 4 poles for them to start at, right? So each of my branches will start at each one of these poles and either get sucked into this 0 here or get sucked out to infinity. Angela, how many infinite zeros do I have?
4? No, it has to be even, right? It's a great question. Can I call for a friend?
Yes, David? Okay, how many finite poles do I have? Finite poles. Okay. How many finite zeros do I have?
1.
Okay, so there must be 3 infinite zeros.
But you have a infinite pole though.
Where's my infinite pole?
At the top, the s plus 3. So you're gonna have to get another 4 infinite zeros to compensate. Have 4 infinite zeros to compensate. The s plus 3 goes to, right? You make s equal to infinity. You get infinity on the top. Or you're supposed to cancel them.
I need to get clarification on that. I think my thinking is that it cancels because I know for certain that there are only 3 finite or infinite zeros.
So if you have a polynomial on top of a polynomial, you can't have both infinite poles and infinite zeros?
I think you first need to do L'Hopital's rule to get rid of it and then plug in the infinity. But that
You see what I'm saying?
also wouldn't, yeah, no, I absolutely see what you're saying. That wouldn't make sense because then you would never have,
Both at the same time for 2 polynomials.
Yeah. okay, I need to look into it more. Thank you for bringing that up. I'll clarify that in our next class. But based on our finite poles and zeros, we know that there at least has to be 3 infinite zeros to balance out the number of poles. Okay? So there must be 3 infinite zeros. Okay, we need to keep in mind our symmetry rule, but the symmetry rule doesn't necessarily allow us to add anything to the graph, so I'm just going to put in, let's keep in mind symmetry. Rule 3 tells us about our real axis branches. Okay, so our real axis branches exist to the left of an odd number of symbols. So should I draw it on this part of the real axis? Yes or no? Is this section to the left of an odd number of symbols?
Say it again?
Can you define what you mean by odd number of symbols?
Yes. This is a pole.
Uh-huh.
That's one symbol.
Agreed.
That's an odd number. So I put a branch here. When I'm to the left over here in this section, there are 2 symbols to the right, so I do not add a branch to the real axis. When I am in this section, I am to the left of 3 poles, so I have a branch there. When I'm in this section, I'm to the left of 4 symbols, pole, 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 0, so there's no branch on the real axis. And when I am out here, I am to the left of 1, 2, 3, 4, 5 symbols. A pole is 0, pole, pole, pole. So there is branch here on out because there's never any other symbol. So one of my infinite branches extends perfectly along the real axis.
They cancel. You're supposed to cancel them. Yes, if you have 2 polynomials, you'll never have both. Okay, so if you have like s over s plus s to the 4th, you just delete the top one, 1 over s cubed.
So you'll either have infinite poles or infinite
If you
zeros,
have
but
2
never
polynomials,
both?
If you have 2
okay.
If you have something more complex, then you can have both.
Yeah.
If there's 2 polynomials, then you can only ever have one.
Okay,
Either have
that makes sense.
zeros or infinities.
Okay, that makes sense. Thank you. I appreciate that. Okay. All right, so do we have any more questions about the real axis branches? Yeah.
If you then say another one goes in the other direction, does it have to be symmetric?
No. It's not symmetric left to right. It's symmetric up and down. So if I have, and I will, if I have a branch that goes like this, the symmetry says I also have to have a branch that goes like that. So symmetric top to bottom, absolutely not symmetric left to right. Good.
That only counts as 1.
No, that counts as 2.
That's 2.
Those are my 2 other infinite branches. Yep. Okay. Now let's look at starting and ending points. I'll put it up here. Okay, we know we start at, branches start at poles and end at zeros. Okay, is there already one branch that starts at a pole and ends at a 0?
Yes.
Which one?
The second one?
Yeah, the middle one. Yeah. You could have argued that the one extending to infinity does as well because it goes out to that infinite 0. But yes, so this branch already starts at a pole and goes to a 0. This one already starts at a pole and goes to an infinite 0. We know we have 2 infinite zeros left. So this pole has to be going this way and then either off to infinity that way or off to infinity that way. And this one must be going this way and then off to infinity that way or that way. Okay. So we can go ahead and say we know that it does something like this. But of course, we need to do our final step to figure out which angle it shoots off at. We know it shoots off to infinity some way, but we don't know what angle or what line it follows. Okay, so let's do that last step, that behavior at infinity. 5 says that we know we have a sigma A, which is our real axis intercept it's actually for all of the asymptotes in this problem. Our real axis intercept will be the same, which is the number of finite the sum of the finite poles minus the sum of the finite zeros over the number of finite poles minus the number of finite zeros. Okay, what were my finite poles? We can look back up at our transfer function here. Finite poles?
0, -1, -2, -4.
Yes, 0, -1, -2, -4. So, finite poles. 0, -1, -2, -4. Minus, what were my finite zeros? -3. How many finite poles did I have? How many finite zeros did I have? 1. Okay, this should equal out to a -4/3. Okay, so the real axis intercept for our asymptotes happens at -1 1/3. So somewhere about right here. Okay, that's the real axis intercept of our asymptotes. Now we need to figure out what angle to draw those linear asymptotes at. We know they go through that point, but what angle do they go at? It's the real axis intercept of asymptote lines. Okay, theta A, that equation was 2k plus 1 pi over the number of finite poles minus number of finite zeros, where k is 0, 1, 2, up to however many asymptotes we know we need. So in this problem, we know that there are 3 branches that go out into infinity, so there must be 3 asymptotes. So in order to find out the angles, we'll need to do this equation where we plug in k equals 0, we'll need to plug in k equals 1, and we'll need to plug in k equals 2. Okay, if we plug in k equals 0, what do we get for theta A? Well, we'll have just 1 times pi in the numerator over 4 minus 1 is 3. Okay, and this is in radians. Now let's plug in k equal to 1. Theta A is 2 plus 1, which is 3 pi, over 4 minus 1 is 3. So this is just pi. And k equals 2, theta A. So I'll get 4 plus 1, which is 5 times pi, over 3. Okay, so let's look at what happens to our asymptotes. I'm going to draw my asymptotes in red. We know that pi is half of the circle. Pi over 3 is just the first third of that half. Okay, so I know that I have one asymptote line that goes like this, where this angle here is pi over 3. That's one asymptote line. Another one is, oh, surprise, surprise, it's at pi. Did we already know that?
Yeah.
We already knew that. We already knew that that one branch extends towards infinity on the real axis line. So I have an asymptote that technically goes out this way. And then the other one is 5 pi over 3. So if I go 1, 2, 3, 4, 5 thirds, I have one that goes out this way. Ah, did we already know that that one existed? Yeah, because of what rule? Symmetry. Very good. Okay, so those are our asymptotes, but what does this mean about the branches? Well, it means that one of these poles has to go off in this direction, following one asymptote, and one of them has to go off in this direction, following the other asymptote. Yes, David?
You know they're gonna start from like in the middle, is that just a given?
Because they have to start at poles and end at zeros. I don't actually at this point, I don't know where along the real axis they leave. It could be, you're absolutely right. At this point, I don't know. It could be that they're like a little over closer to the one pole than the other. It could be like that. I don't know yet. But for the rough sketch, just put it on there. Yeah. Amari. It's usually the first one because we're usually talking about proper systems where the denominator has a higher degree or higher power, which means that there are more poles than zeros. If there are more zeros than poles, it goes back to what Nadal was saying about how you will end up with the opposite being true. You'll end up with more zeros than poles, and then you will probably, I think, have infinite poles, which is also possible. It is possible to have an infinite pole. But of course, that means that your branch starts at infinity, which is a little bit weird. For this class, I'm not going to test you on infinite poles, but you absolutely will see infinite zeros. Yep. I hope that answers. Okay. Yeah, Josh.
How did you know which values to k to substitute in? Was that like predetermined in the problem?
Values of k. Did I, in any of this, did I assume any values of k?
So I think they can't be theta.
You mean this k,
Yes.
not the gain.
Correct, yeah.
Okay, sorry. Yeah, they probably should use a different letter for that. Sorry. Shouldn't copy out of the book. Yes, this k is not the same as the open loop gain.
Very different case.
Sorry. How did I know? Well, I knew based on the number of infinite zeros that I had, that I knew how many branches had to extend into infinity. And so I needed to keep plugging in integers for k until I had the right number of asymptote lines. Yep. If you wanted to be very ritualistic about it, I could tell you that it's like the number of poles minus the number of finite poles minus the number of finite zeros minus 1. But you just keep plugging in values of k until you have the number of asymptotes that you know you need based on the number of infinite zeros that you know you have. Cool? Cool?
So would you always go to 0, 1, and 2?
Yes, yeah, you always start at 0 and then you increase by integers until you have the number that you need. Anything else? Okay, so that's the end of our rough sketch section. What we're going to cover next is how to refine this sketch. And I went a little off of the beaten path. This lecture doesn't follow quite as parallel with Dr. Hubicki's lectures as previous ones have. So it may be that I overfilled today's lecture, and in which case the example at the end you can find in the lecture notes. Yeah,
I
Angela.
might be getting ahead of myself, but how
Yep.
do you get the through Locus sketch where it's like doing the little semicircle jumping between the either poles or zeros? Is there?
We're going to do an example.
Okay.
We're actually going to do 2 examples of exactly that. Yep. But if, based on what you know already though, it would have to be the case that none of the branches go off into infinity, right? Unless it like shoots off to the left, which it might. It might still do that even if it loops. But you would probably have two poles together with real axis poles in the middle. So they need to shoot off, but they're not going to go to infinity. So they have to come back.
Okay.
Like the finite zeros exist, but they're not in the right spot for the poles to go directly to them. Like they need to go towards each other first and then split off, but come back.
Okay.
Does that make sense? Okay. Okay, so what we're going to talk about next are, I'm going to give a specific name to these points that David talked about, right here. This particular spot where I had real axis branches that suddenly became no longer real axis branches. They shot off from the real axis, either to up or down, either way. We're going to call that a breakaway or a breakout point. Okay, breakout point is where it leaves the real axis. And then the next thing we're going to talk about is what Angela just asked about, which is a break-in point. So if at any point a branch was off of the real axis, but it returns to the real axis as you increase values of k, that will be a break-in point. So break out and break in. So breakaway point, a point where the root locus leaves the real axis. Break-in point, a point where the root locus returns to the real axis. So it turns out that the rule here for this refinement is that at the breakaway or break-in points, the branches of the root locus form an angle of 180 degrees over n with the real axis, where n is the number of closed loop poles arriving at or departing from that point. So if we have two branches coming in at the same break-in point, they will come in at angles positive 90 and negative 90, or 90 and 90. Okay, they'll come in at 90-degree angles in order to satisfy this rule. So let's look at an example. Let's put 2 zeros over here, 2 poles over here. All right, where should I draw my real axis branches? Should I draw a branch here?
Yes.
How many symbols are to the right? 1. So that's an odd number. So yes. Should I draw it in this section?
No.
No, because there's 2 symbols to the right. That's an even number. I have no branch there. What about between these 2 symbols? Right. I am to the left of 3 different symbols, so I draw it here.
I thought the branches only start at poles.
They start at poles and they end at zeros. So what's happening here is that the branches that start, let's trace it here. The branch that starts here, for instance, goes out here. It's going to shoot off of the real axis, and it's going to break in. And so really the k values are increasing in this direction. Yep. Good question. Very good question. That's why I enjoy having you in class. I gotta stop. I gotta stop. Okay. Alrighty. Okay, so exactly like Nadal said, we have 2 branches that are starting from our poles. So they initially go towards each other because we know there has to be a real axis branch in that section. So at some point, they must split off of the real axis. They must go up or down in some different angle. We're not quite sure. And then they must return in order to terminate at these 2 zeros. Okay? So what angle do they leave the real axis over here? 90, right? They leave at 90 degrees because there are 2 branches leaving, and we divide our 180 degrees by 2. So I'm going to leave at 90 degrees. And then when I break in, I'm going to break in somewhere between these two zeros. What angle do I break in at? 90, right? Because I'm dividing that 180 degrees by the two branches that are coming in at the exact same point. So you still won't know for certain that this is like a perfect circle, but it is roughly what happens is it's going to circle about like this. It's going to circle about like this. And that tangent line where it enters the real axis is 90 degrees. So 90, 90.
So if you have three branches leaving, and for these symmetrical, does one of the branches have to be along the real axis?
Yep, 100%. Yep. Okay, so we know what angle they break away at, but we don't know where they break away at. Going back to David's question, I've drawn it as though the breakaway point is perfectly halfway between the poles and perfectly halfway between the two zeros. But that's not actually the case. We don't know for certain where they break away and break in. So how do we figure that out? Looks like I am ahead on my notes. How do we figure out where along the real axis the breakout points occur? Let's think critically about what's happening over here. Our points are perfectly on the real axis. There are no imaginary components whatsoever. And as they start out at the poles, and as K gets bigger and bigger and bigger and bigger and bigger, I'm approaching this breakout point. Which means that K must be at a maximum just as we're breaking off. So we need to find the maximum K value that keeps us on the real axis. And for that real value, that will be our breakout point. So for instance, if we were to maybe draw a graph, and we said, let's look at plugging in values of S that are on the real axis. So this is just the real component of S. And let's say we plugged in values from maybe negative, whatever this number is. I didn't even give a number for this example. Maybe this is -4, and maybe this is -3. And I said, okay, I'm going to plug in values between here and here, and I'm going to find the K value that goes with that point. Well, K should start out as 0 when I'm at those poles. And as K gets bigger and bigger and bigger and bigger, it goes up and up and up and up and up and up, and then it ceases to exist on the real axis anymore. So if I have a function and I want to find its maximum, what do I do mathematically? Take the derivative and set it equal to? Right, so I'm wanting, on this graph, I'm wanting to find what is the sigma value that results in a slope of 0 of this graph. Which means that we would need to find a function for K in terms of this sigma. Well, that's fine. In our previous section, I didn't actually go into this equation when I covered the magnitude criterion, but this is one of the equations that leads to the magnitude criterion equation that I gave you. Suffice it to say that K is equal to -1 over G of S H of S. So this is really like K of S. But if I plug in only real values of S, I get K sigma equals minus 1 over G of sigma, H of sigma. If I take the derivative of this and I say d K of sigma d sigma, and I set it equal to 0, and I solve for sigma, this sigma will result in a maximum K value, which means that this sigma is the location of our breakout point. Let's do a little intermediate example here. Let's say I have an H of S, G of S equals 1 over S plus 1, S plus 3. So if I were to really quickly sketch real imaginary, I have a minus 1, minus 3 pole, 2 poles. I draw the real axis branch between them because I'm to the left of a single pole. I must have 2 infinite zeros because I've got not enough zeros for my branches to go to. So they must shoot off into infinity somewhere. Oh, hold on. Yeah, okay. So they must shoot off into infinity somewhere. I'm not going to worry about the angle. But let's try to find where that point is, that the breakout point happens. So we know that K of S is equal to minus 1 over G of S, H of S. So 1 over S plus 1, S plus 3. I can rearrange this into minus S plus 1, S plus 3. I can FOIL that out to make it easier to take a derivative. 1s3 s squared s3 s3. So K, I want to plug in only a real value of S, so just the sigma portion, should be equal to minus sigma squared plus, minus 4 sigma minus 3. I can take a derivative of this with respect to sigma and set it equal to 0. I should get minus 2 sigma minus 4. I should get that sigma is equal to minus 2. Is that a value between the 2 poles? Yep, makes sense. It just so happens that this one is halfway between the 2 poles, but it is not always halfway between. In fact, our final example will show and prove that it's not always exactly halfway between. Okay, now in this problem, we didn't have any zeros. So taking the derivative of this expression was very easy. But if we had zeros, we would end up finding ourselves needing to take a derivative of something that was like s cubed plus 4s plus 2 over maybe s to the 5th plus 3s squared plus 8, right? We would end up with a fractional, a fraction made up of polynomials, so polynomial on the top and the bottom. And in this case, if we need to take that derivative, we need to remember our derivative of fractions rule, which says that the derivative of h of sigma over, we call the numerator the high and the denominator the low. This is equal to low d high, thank you, Angela, minus high d low over what?
Low.
Low over low. Did anyone else have an insane calculus teacher who listened to like Calculus the Musical? She had a CD that she made us listen to like every day. It was like songs, like opera songs of these rules. It was psychotic, but it worked, and I hated that it worked. Okay, so you'll need this for this last example. All right, last example. We're going to pull it all together and draw a detailed root locus of the following system.
So if you're curious, actually the general case, even if it's ugly stuff, like not polynomials, it's always the same. If you have like a proper transfer function, always just infinite zeros. You'll never get infinite pole, no matter how ugly.
Right, that's what I told Amari. Is
No, even-
it depends on being proper or not,
Even if it's not a polynomial.
even if it's not a polynomial.
Even if
Yeah,
it's
yeah.
disgusting.
Yep.
Is that S minus 5 on the numerator?
S minus 5, yes, and 5 is a terrible choice when you're working with S's, but that is a 5.
Thank you.
I'll try to accentuate it. When I was working this problem beforehand, I actually messed up my 5 as an S, so. Okay, here we go. Let's look at, let's try to figure out the open loop transfer function. What type of simple block diagram form is this?
Series.
Cascade, which means that we do what to make them into one? We multiply them. Very good. Okay, so this should be k s minus 3, s minus 5 over s plus 1, s plus 2. Just to double check, we'll go ahead and do our closed loop 2. We'll do all of this grossness, k, s minus 3, minus 5, s plus 1, s plus 2, over 1 plus, k, s minus 3, s minus 5. Okay. I think that's the limit of this working, John. So if we were to have non-unity feedback, I think that's when you'd get a different number of closed loop holes. Yep. Okay, highest power of S in the denominator. 2 means that I have how many closed loop poles? 2. Let's go ahead and start drawing. Real. Okay, I have a pole at minus 1 and minus 2. Minus 1, minus 2. I have a 0 at 3 and 5. Something like this. I can immediately do my real axis branches. Here. Nothing in the middle. Here. Nothing to the left. So somehow these branches that are starting at these poles on the left, they have to get over to the zeros on the right. Okay, so we know that they're going to do something like this. But this is a detailed sketch, so we're going to go ahead and try to figure out where are these breakaway and break-in points. So this would, of course, be a breakaway point. And this is a break-in point. We can go ahead and tell what angle they go off at, too. What angle? 90 and 90, yep. So there is some tangent here where these branches break off. Very similar to the last example that we did. And then if we want to figure out where they are, we need to find K of S equals minus 1 over G of S, H of S. Okay, so this should be the same as just taking the negative inverse of my transfer function. So I should get minus S plus 1, S plus 2 over S minus 3, S minus 5. And if I plug in only real values of the S-plane, I get, and I'm actually going to go ahead and FOIL this too. So a couple of steps happening here. I'm plugging in.
Quick question.
Yes, ma'am.
Any reason why K isn't in the denominator?
We're solving for K.
Oh. But like in our open loop, did it just get moved over?
Mm-hmm.
Oh. never mind.
It's how we arrive at that equation is we solve for K. Yep. Because we want we want an expression for K in terms of S so that we can take a derivative of it.
Okay.
Yep. Okay, so this goes to sigma minus sigma squared minus 3 sigma minus 2 over sigma squared minus 8 sigma plus 15. All right, and I want to take a derivative of this and set it equal to 0. But I have sigmas in the numerator and sigmas in the denominator, so I've got to do my low d high minus high d low over low low. So give yourself some space. It's going to take a lot of terms here. So low d high minus 2 sigma minus 3 minus high d low, and I knew I was going to run out of space, and I still did it. D low. All over low low. Ugh. I need to figure out where this is equal to 0. So we're going to have to FOIL like fiends. If you need to leave for an exam, feel free. Do you want me to work through all the FOIL, or do you want me to just tell you what you get?
Just tell us the answer.
Okay, all right, fine. Happy to do so. Okay, we should get 0 equals 11 sigma squared minus 26 sigma minus 61 over low low Of course, if we multiply by the denominator, we just get 0 equal to the numerator. So really, we just need to find the sigma that makes the numerator 0. So equals 26 plus or minus square root 26 squared minus 4 times 11. Of course, here I'm doing the quadratic equation. You'll end up with sigma equal to minus 1.45 and sigma equals 3.82. So notice here that I didn't get minus 1.5. It was a little bit off of 1.5. So it's not perfectly between the two poles. And then I got 3.82, which is not the halfway point between 3 and 5. If it were the halfway point, it would have been 4, but it's not. Angela?
And just for like logical reasons, k would never have like a imaginary component to it, right?
We are specifically looking for the maximum k that results in a real value because it's the last one before I break out.
Okay.
Yeah.
So we know we did something wrong there.
Yes.
Okay.
Yep. That's why I plug in only sigma. Yeah. I actually kind of glossed over this, but the break-in point is not actually a maximum k anymore. It's actually the minimum k before you get back onto the real axis, but it's still an extrema of that k equation. So finding the derivative, setting it equal to 0 will also find that point for you. But just in case you're worried about max versus min, it works out the same. Okay, so last thing I'll do is I'll put the breakout point. So I am just shy of 1.5, so I'll put it over here. And I'm just shy of 4, so I'll put it like right here. And then I know that I go, woo, just like that. If you don't do the sound effects, I'm taking points off. Woo. All right. We made it through. You did it. We're done with class. You made it through another week. Angela?
Do we care about the maximum, like, imaginary component?
Height of the branch? Not really. What we might care about is where it crosses the imaginary axis.
Okay.
Why would we care about that?
Because then it's going to be unstable if it's on the right.
It's going to be unstable, yes. We absolutely care about the K values that make us unstable. So another thing that you can read about in the book I'm not going to cover is finding where you cross the imaginary axis, which is in your brain should be like, woo, woo, bad things are happening if I'm crossing the imaginary axis. Have a good weekend. I'll see you next week. Homework 4 is posted.